Hello everyone. In this lesson, we're going to be looking at derivatives and rates of change. So to do this, we're first going to begin by looking at the slope of a line through 2 points. So suppose that we have 2 points, x1, y1, and x2, y2. And if we want to know what the slope is between these 2 points, right? So let's say we have one point here. This is x1, y1, and this is x2, y2. We want to know what is the slope between these 2 points. Normally what we would do is we would try to figure out what is the rise over run, or the rate of change of y over the rate of change of x. And the reasoning behind this is, let's say that this is on our Cartesian plane, and we want to know how far have we moved in the y direction. So what we would do is we would figure out where is y1 and where is y2. We would take the distance from y2 to the origin. Then we would take the distance from y1 to the origin, subtract that off, and we're left with the distance between these two. And then we would do the same thing for x1 and x2. And this would give us how much we've moved in the y direction over how much we've moved in the x direction. So this is then going to be y2 minus y1 over x2 minus x1. And since we have that f of x is usually can be written as y, this can be written as the change in f of x divided by the change in x. So what does this slope actually represent? Well, it represents the average rate of change between 2 points. So if I wanted to know what is the average rate of change from this point to this point, I could just consider the slope between those 2 points. So now we're going to learn about tangent lines. The word tangent comes from the Latin word touching. A tangent is a straight line that just touches a curve at one given point. And the slope of a tangent line represents the instantaneous rate of change at that single point. So let's say, for example, that we have some function, something like this. This means that if I wanted to take the tangent line at this point, it would be the slope at that particular point. Or if I took one here, it'd be the slope here. Or if I took one here, it would be the line that goes through right here. It is a line that touches just at that single point, telling us what the slope is at that exact moment, that exact point, giving us the instantaneous rate of change. So remember previously when we talked about dropping a ball from a tower, and if we knew the distance that it fell and the amount of time, we could figure out the average rate of change. Well, now with the idea of a tangent line, if we could map out the function that describes that ball falling from a tower, we could figure out what the instantaneous rate of change is at any given time, not just the average over the entire ball drop or between 2 time periods. Now to do this, what we're going to be doing is we're going to be looking at how do we find derivatives. So we call the slope of a tangent line to that given point on a curve its derivative. And the process of finding a derivative is called differentiation. Derivatives are called instantaneous rates of change. And as an example, velocity is the derivative of position. And acceleration is the derivative of velocity. So for example, if we took the derivative, it would tell us the amount of change of that particular variable. So velocity is the rate of change of position, acceleration is the rate of change of velocity. And we're going to use the notation f prime of x to represent that we are going to be doing differentiation. Now, since the derivative of a function at some given point represents the slope of the tangent line at that point, we're going to be using formulas for slope to find our derivative. So if you remember, like I said, if we have the points x1 and y1 and x2, y2, we would have that the slope, I'm going to write this as m because whenever we do line slope formula, this would be y2 minus y1 over x2 minus x1. Now, if we were to change our y's into f of x to represent their function, then this would become f of y2 minus f of y1 divided by x2 minus x1. Now let's actually look at the slope of a tangent line to some point A. So we'll write this as to A, f of A. And this is the actual point that we want to find the tangent line for, meaning that, if we had some slope, for example, and this is our a value, then we would have some associated f of a or y value with that for that point. So then now what we're going to have is we're going to have our slope m equals the limit as x2 approaches that point x1, basically as it gets closer and closer and closer until it touches it, f of x2 minus f of x1 divided by x2 minus x1. And what's happening now is that we're taking the limit as this slope formula is the points are getting closer and closer and closer. So let's say that this was my x. My x was right here. So I would have some point here. This is my f of x. And pretty much we're taking the limit as this x approaches this a, and our function, our f of x approaches this f of a, and we're getting closer and closer and closer until we are just at that point where we're infinitesimally close to where we're getting a slope at that single specific point. So now what I'm going to do is, because we're approaching this value a, is I'm going to replace my x1 with this. So this is going to then be equal to the limit as x approaches a, f of x minus f of a divided by x minus a. So in this case, all I did was I replaced, instead of saying x2, I'm just calling this x. And instead of saying x1, I'm calling this a. So pretty much as my, originally what was x2 gets closer and closer to x1, or now we're referring to it as my x value gets closer and closer to that a that I'm actually interested in. So then we're going to rewrite this now in terms of the distance between the two. And this formula is going to be the limit as h goes to 0, f of a plus h minus f of a divided by h. And all h represents is the distance between this x and a. So what we're saying here then is, if I'm going to redraw this so it's a little easier to visualize. I'll put them a little further away so you can see what I'm talking about. Let's say that x is right here. And let's say that a is here. So the distance between them is h. So of course, if I get my x, I'm going to have some f of x here. My a is going to have some f of a here. But now, instead of looking at f of a, we're actually replacing this with f of x plus h. Because if I took x plus h, this is the same thing as a. So now this term is going to be f of x plus h. And if you actually watch the review we did originally, this is where we're using what's called the difference quotient. So we're taking the difference quotient from some point x to some point a, where the distance between them is h, and we're taking the limit as that h goes to 0. So let's do an example. The first one we have is we want to find the slope of the tangent line for the hyperbola y equals 3 over x at the point 3, 1. So in this case, first thing we're going to do is we're going to set up our definition of a derivative, which is going to be the limit as x approaches a, f of x minus f of a divided by x minus a. And in this case, our a is that value that we're approaching. So in this case, it's going to be 3, right? We're changing our x value. So in this case, a is equal to 3. So if we look at our function then, our f of x for this is going to be this hyperbola that we had. So this is going to be 3 over x. And now, if I were to plug in f of a into this, so f of a is just going to be f of 3, which is going to be 3 over 3, or 1. So now we know what, for our actual point that we're approaching, we know our x value, we know our y value, and it matches what we have here, so that makes sense. So now let's plug it in to our limit. So we have the limit as x approaches 3, and then I'm going to plug in my f of x. We said our f of x was this 3 over x, minus my f of a, which we just said is equal to 1, divided by x minus a. Well, my a is 3, so we're going to have x minus 3. So now we have this. So now what we need to do is we need to try to solve to figure out what this limit is. We want to figure out what the slope is there. So what I'm going to do is, because I have a fraction subtracting 1, I'm going to get it to a like base. So this is going to be the limit. And don't forget, you leave the limit until you're actually ready to evaluate it. This is going to be 3 over x minus, and then to make 1 in terms of over x, it's going to be x over x divided by x minus 3. And now with this, I can actually split this into two parts. I can have 3 minus x over x, and then times 1 over x minus 3. Now, why is that? Because basically what we're doing is this. We're saying that this is the limit as x approaches 3, and then I'm going to combine these terms together. So this is going to be 3 minus x over x divided by x minus 3, which, of course, we have fractional division. So if you wanted to, you could think of this x over 3 as x over 1. So then I'm going to bring this term here. I'm going to bring this term here. So this is going to cause it to become the limit as x approaches 3, 3 minus x times 1, so that doesn't change, divided by x times x minus 3. And of course, if I have something like this where it's like, I don't know, I'm just going to put 3 minus x over a times b. This is the same thing as 3 minus x over a times 1 divided by b, right? Because if I were to multiply this out, the 1 doesn't change it, and this just becomes ab. So that's what I'm going to do in this case. So this is going to become the limit as x approaches 3, and then I'm going to be left with 3 minus x divided by x times 1 over x minus 3. Now, if I were to try to evaluate this now, this would still be a problem because I have this x minus 3 in the denominator. And if I plug in 3 there, it's going to be 3 minus 3. I'm going to get a 0 in the denominator. And 0 times the x, which is 3, is still going to be 0. So we have a problem here. So what I'm going to do is I'm actually going to pull a negative out of this term here so that I can make it the same as this. So this is going to be the limit as x approaches 3 minus, so this will be minus x becomes plus x. And then 3, I'm going to make this negative 3, right? So you can always check it by trying to redistribute it. This becomes minus x plus 3, so 3 minus x, same thing. And this is going to be over x times 1 over x minus 3. By the way, you didn't have to do this step. You could have left it all together. I just did this so it was a little bit clearer to see. So now what we have is we have this x minus 3 cancel with this x minus 3, and we're left with the limit as x approaches 3, negative 1 over x. So we have the limit as x approaches 3, negative 1 over x. And now we can plug in our 3, and it doesn't have a 0 in the denominator. So when I evaluate my limit, I plug in 3 for x, I get that the slope at this point is negative 1/3. So now what we're going to do is I'm going to use the difference quotient to show that we get the same answer and how it's just a little bit different, but it's the same idea. So that's why I'm going to leave this here so we have something to compare it to. So first we're going to set up our difference quotient, which is the limit as h goes to 0, and I will set up f of a plus h minus f of a over h. Which, by the way, later on, a lot of times I'm just going to write this as f of x because x or a, it doesn't really matter. It is an x value. It's just the value that we're approaching. So if I consider the distance from x to my value a is h, I can use a instead of x, and it's the same distance, just in the other direction, but then it flips sign. It doesn't change anything. So we have this. We still have that a is equal to 3, because that's the value that we're approaching. So we're starting at 3, and then we're changing by some distance h, whether it be to the left or to the right, right? So that's why it doesn't change anything. So first things first, I'm going to figure out what is f of a plus h. Well, if our f of x was 3 over x, and what we have here is we are going to be plugging in, right, because our a is 3, this is going to be 3 plus h. We are going to plug it into this function right here, and we're going to get 3 over 3 plus h. So that's our f of a plus h, or f of 3 plus h. Then I'm going to find my f of a. So my f of a, which is just equal to f of 3, which, just like we did before, is 3 over 3, or 1. And now what I'm going to do, I'm going to take these, I'm going to plug them into this limit here. So I'm going to bring the limit down here. So this is the limit as h goes to 0, and I'm going to plug in f of a plus h, which is this term right here. So this will be 3 divided by 3 plus h minus f of a, so minus 1, divided by h. And I can't take the limit to begin with, because if I evaluate the limit now, I'm going to have a 0 in the denominator. So I have to do some rearranging to get it in terms that I can actually do some cancellation to solve for it. So just like before, I'm going to change this 1 so it's in terms of whatever the denominator is, so I can combine them together. So this is going to be 3 plus h. So this is going to be the limit as h goes to 0, 3 over 3 plus h minus 3 plus h over 3 plus h. And then this is all divided by h. And now that I have these two in terms of the same denominator, I can combine these together. So this is going to become the limit as h goes to 0. So 3 minus 3, and then I could consider it minus 3 plus h, which if I were to distribute that negative, it would be minus 3 minus h. I'll leave it this way for now. Divided by 3 plus h divided by h. Okay, so now we have this so far. Now I could consider this as the same thing as, right, if I did fractional division, this h is just going to come over here, you got a 1 over here. So this is kind of the same thing as saying times 1 over h. So I'm just going to get rid of that term so it's a little clearer what we're looking at. So now what we're going to do is we're going to cancel out these 3's. And of course, remember, this negative goes to this h. So I have the limit as h goes to 0 minus h divided by 3 plus h times h. Right, because I had the times 1 over h, so it's the same thing. So this h is going to cancel with this h. And now what I'm left with is the limit as h goes to 0 minus 1 over 3 plus h. Now at this point, I can evaluate, because as h goes to 0, I can plug this in here and I won't get a 0 in the denominator anymore. So now that I'm evaluating, I don't need to carry my limit over anymore. So this is going to be negative 1 over 3 plus 0, or negative 1/3, which if you look at what we got for our original answer, it matches exactly what we got. And by the way, so in this course, generally this is the form that we're going to be using, not this one, because this actually has some properties that make it a little easier to solve. I know it seems like we're basically did the same thing, and generally it is true, but there are certain times where this will actually be a little bit more intuitive to solve. Okay, now that we've found the derivative, remember, this derivative is our instantaneous rate of change at this point, a equals 3. This means that this is the slope, but we want to figure out what the tangent line is. So what we're going to do is we're going to use the point slope formula. So we're going to use our point slope formula, or point slope formula line, which is going to be y minus y1 equals m times x minus x1. And we're going to plug this in, and we're going to solve to determine what our line is. So first things first, we're going to plug in our slope, and we're going to plug in our x and our y for that point that we're at. Remember, because this is the instantaneous rate of change at this point, 3, 1. So then this becomes y minus, our y value is 1, equals negative 1/3 x minus 3. And this is going to allow us to solve for our slope-intercept form of our line. So first thing I'm going to do is I'm going to distribute this negative 1/3. So this is going to be y minus 1 equals negative 1/3 x. I don't know why I put the x down here. 1/3 x. And then minus 1/3 times negative 3 is going to give me positive 1. So plus 1. And now what I'm going to do is I'm going to bring this 1 over. So I'm going to add 1 to both sides. So plus 1, plus 1. This is going to be y equals negative 1/3 x plus 2. And this is the slope for our tangent line at the point 3, 1. It has a slope of negative 1/3, and then we could draw the rest of the line using this form. Next, we're going to do an example where we're going to find the derivative of this function, f of x equals x squared minus 8x plus 9 at x equals a. So first thing we're going to do is we're going to say, okay, we want the derivative of fa, which is going to be our limit as x approaches a f of x minus f of a divided by x minus a. So we have our f of x here, so I'm going to plug this f of x in to see what our limit becomes. So in this case, we have the limit as x approaches a, x squared minus 8x plus 9 minus, and now I'm going to get f of a, which is the same thing, but instead of x squared minus 8x plus 9, it's going to be a squared minus 8a plus 9. But remember, I'm subtracting this. So what I'm going to do now is I'm just going to flip all the signs. So this is going to be minus a squared plus 8a minus 9 divided by x minus a. So looking at this, we have plus 9 and we have minus 9 that we can cancel. So rewriting this, we have the limit as x approaches a, x squared minus 8x minus a squared plus 8a divided by x minus a. Now, what is this equal to? Well, we could try to solve this. We could try to, for example, put the 8's together and then pull them out. We could put the x's together, or we could put the square terms together and try to do something with that. But really, I wanted to show you that this is sort of the pitfall of using f of x and f of a. So now what we're going to do instead is let's actually look at why it's simpler to solve this using our difference quotient where we had h going to 0. So using the difference between the 2 points rather than the 2 points themselves. So rewriting this, we would have f prime of a is equal to f of a plus h minus f of a divided by h. And then we're going to do the same idea. But first thing we're going to do is we're going to figure out what is our f of a plus h. So if we have f of a plus h, this is going to be the same thing as plugging a plus h into every one of these x values. So this is going to be a plus h squared minus 8 times a plus h plus 9. So of course, now I'm going to factor this, and I'm going to distribute this, and we'll figure out what this is. So this one I'm going to do FOIL it. So first I get a squared. I'm going to do outer, inner, which is going to be ah. So I'm going to have plus 2 ah plus h squared. For this, I'm going to distribute the negative 8. So negative 8a minus 8h, and then plus 9. And now what I'm going to do is I'm going to combine like terms if I have any. It looks like I don't have any, so that's perfectly fine. So now let's figure out what is our FA, right? We're looking for FA now. So FA, same idea, except for I am plugging in a into each of these x's in my original function. So this is going to be a squared minus 8a plus 9. Now let's bring these and put them back into our limit. So this is going to be equal to, I forgot to write my limit as h goes to 0. So this is going to be equal to the limit as h goes to 0. I'm going to plug in my f of a plus h. This is going to be a squared plus 2ah plus h squared minus 8a minus 8h plus 9. And then, remember, it's minus f of a. So all these terms, a squared becomes minus a squared, negative 8a becomes positive 8a, and plus 9 becomes minus 9. So this is going to be minus a squared plus 8a minus 9. And then all of this is divided by h. And now let's see if we can do some any cancellation. Well, we can, right? So we have a squared, we have minus a squared. We have 9, we have minus 9. We have minus 8a, we have plus 8a. So we are left with the limit as h goes to 0, and then we have h squared plus 2ah minus 8h. So we have h squared plus 2ah minus 8h divided by h. So every term here has an h. So what can I do with that? I can pull the h out. So this is going to become limit as h goes to 0, pull out my h. So if I pull an h out of h squared, this is going to be h plus. If I pull an h out of 2ah, this is going to be 2a. If I pull an h out of minus 8a, it's going to be minus 8. Divided by h, these h's cancel, and I'm left with the limit as h goes to 0, h plus 2a minus 8. I can evaluate my limit now by plugging h in. So I plug in 0, and I'm going to get that this derivative is equal to 2a minus 8. So pretty much what this is telling us is that our derivative is dependent on what that a is. So if I'm approaching the point 3, it would be 2 times 3 minus 8, and that would give me the slope at that point. If my a was 7, it would be 2 times 7 minus 8, and that would give me the slope at that particular point. So the slope is different based on that initial point that we are going to. So let's find the tangent line using this, and we're going to be going through the point 3, negative 6. So we want the tangent line to the formula y equals x squared minus 8x plus 9, and going through the point 3 minus 6. So if we were to look at our f prime of a, that's our slope, that's our derivative at that point. If we were to plug in 3 into this, f prime of 3, this would be 2 times 3 minus 8. So 6 minus 8 gives us a slope of negative 2. And now we're going to use our point slope formula to figure out what is the equation for our line. So we're going to have y minus y1 equals mx minus x1. I plug in my negative 2 for my m, so I'm just going to put my slope in first. And this is going to be x minus, my x value is 3. And then y minus, my y value is negative 6. That's going to be plus 6. So then I'm going to distribute that negative 2. So this is going to be y plus 6 is equal to minus 2x. And then minus 2 times minus 3 is plus 6. So when I subtract 6 from both sides, I'm going to be left with y equals negative 2x. So this is the line that describes this, this particular derivative at the point 3, negative 6, is that it is the line y equals negative 2x. For our next example, we want to find the tangent line for the graph for y equals gx, where at x2, so at x equals 2. So if g of 2 is equal to negative 5, and if we have a derivative g of 2 at 2, which is equal to 4, how can we find this line? Well, looking at this, remember that g of x is really just saying the function of x. You could think of this like your y. So we specifically said we're at x equals 2, and when I plug in 2 into this function, I get a y of negative 5. So we're really asking, we want to find the tangent line at 2, negative 5. With a slope, right, because that's what this prime means, is that this is the slope at 2 for this function g of x, which is equal to 4. So we can plug this directly in and we can solve for our tangent line. So we have y minus y1 equals m x minus x1, and then we just plug in our x and our y values, we plug in our slope, and then we can solve for our line. So this is going to be y minus negative 5, so y plus 5, equals m, it says is 4, x minus, our x is 2, so x1 is 2. I'm going to distribute this 4, so we get y plus 5 equals 4x minus 8. I'm going to subtract 5 from both sides, so this is going to give me y equals 4x minus 13. So if you already know what the slope is, and you have a particular point that you're going through, you can actually directly solve for the line, right? So in this case, this was the information I gave you. We had that y is equal to some function g of x, and we were at the point x equals 2. Now, we gave you the output of that function, so g at 2 is equal to negative 5. So that's us saying if we plugged in 2 into this function, we get a y of negative 5. And then we even gave you the derivative at that point, meaning that at the point x equals 2, we know that the point is actually 2, -5, and it has a slope of 4. So there we have all the information, because to use the point slope formula, you need 3 pieces of information: your x value, your y value, and your slope at that point. Next, we're going to find our tangent line for y equals f of x at the point 6, 2. So in this case, instead of giving you the function at this point 6 and telling you it's equal to 2, we're just giving the y value. So we're giving you the points of our x and our y here. And we're saying that it passes through 0, 1. And what we want to do is we want to find, we want to find f6, and we want to find f prime at 6. We want to find the function at 6, and we want to find the derivative at 6. So what we're going to do in this case is we have 2 points, right? So we're going to go back to that. Our first point we have is 6, 2. So we have a point 6, 2, and we have another point 0, 1. And we want to figure out what is the difference between the two. So in this case, we're going to have that our slope is going to be y2 minus y1 divided by x2 minus x1. Well, y2 is going to be 2 minus y1 is going to be 1 divided by x2 is 6, x1 is 0. So we're going to get 2 minus 1 over 6 minus 0, or 1/6. So now we have the slope for our line. This is f prime of x, right? Because our slope is our derivative. We have our derivative, which is going to be the slope, and our slope is 1/6. And now that we have this slope, we have a point, we can actually find the formula for our line. In fact, I'm going to show you that we can actually do it using either of these. So the first one we have is y, well, first of all, let's write down our formulas. Y minus y1 equals m, x minus x1. So the first one, I'm going to plug in 6 and 2. So I have y minus 2 equals 1/6 x minus 6. So of course, if I were to distribute this 1/6, this becomes y minus 2 is equal to 1/6 x, and then minus 6 times 1/6 is going to be minus 1. I'm going to add 2 to both sides, and this is going to become y equals 1/6x plus 1. Now, what if we had plugged in 0, 1 instead? Okay, so we have y minus, my y is 1, equals m, which is 1/6, x minus, my x1 is 0. So this is going to be y minus 1 equals 1/6 x. Add 1 to both sides, and I get y equals 1/6x plus 1. And you will see that these two are exactly the same. So if you have your slope and you have a single point, as long as it is on that function, then it will give you the line, the tangent line at that point. If I have 2 points and they're both on that same line, in this case, because this is a line, then it is going to be the same regardless of which point I choose, right? Because if I took the tangent line here, it's the same as the tangent line right here, or it's even the same as the tangent line here. It's the line because the tangent line is the same on all of them because it's constant, right? So this is the thing, is that the tangent represents the rate of change, and in this case, it's constantly changing at a constant rate. So therefore, no matter what point I pick on this line, I will get the same formula for this line. If I had a function that was not changing at a constant rate of speed, for example, let's say we had something like this, this really doesn't work, because if I have a point here, my tangent's going to be something like that. If I have a tangent here, it's going to be something like that. If I have a tangent here, my line's going to be something like that. If I have a tangent here. So notice each of these would have a different line. But if it's a line, which means constant rate of change, this does work. Any point on the line will give you the same tangent line. So that's it for our introduction to derivatives and how we would solve them using our basic definition of what a derivative is, which is a limit as the distance from some point x gets infinitesimally close, so basically as h approaches 0, to that a value of interest. And as that happens, our f of a plus h, which is f of a plus the distance between the 2 points, as that distance becomes closer to 0, they become they merge kind of together, right? So f of x becomes similar to your f of a. And then from there, we were able to solve for what the instantaneous rate of change is. In our next lesson, we're going to be looking at what are some rules we can use to actually make calculating derivatives a lot simpler, a lot faster, and allow us to do a lot more complex derivatives. Because you can see like the way that we're doing it, this, by the way, is true. It always works. But sometimes if we have an overly complex function or set of functions we're trying to take the derivative for, then it might be very difficult because just very complex algebra to get it into the form that will allow us to eventually solve it, especially if we're trying to solve it analytically. Now we're going to be looking at rules on how can we solve basically any derivative for any function, no matter what it is. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.